Continuing on with our topic of environmentally friendly airspace operations will be Yoon Jung, Associate Principal Investigator of the Next Gen Concept and Technology Development Project under NASA's Airspace Systems Program. He joined NASA in 1998 and has been involved in various terminal, airspace, air traffic management research projects. Before NASA, he worked as a senior engineer at Advanced Rotorcraft Technology in Mountain View, California. He earned his BS and MS degrees from Seoul National University and a PhD in mechanical engineering from the University of California, Davis. And he'll be speaking to us about fuel consumption and emissions from airport taxi operations.
All right, good afternoon. Well, what I'm going to talk about today is emphasis on the surface operations in terms of environmental impacts. A lot of discussions on en route and airspace environment, but the surface is as important as in terms of fuels and noise and emissions. All right, so there are some statistics I'd like to share with you. About 20% or 26% emissions are produced during the landing and takeoff cycle or LTO cycle for flights over 800 kilometer or 500 miles range. This is a study done on 40 airports in Turkey airports. And LTO cycle basically includes final approach and landing, taxi in and taxi out, and climb phases of flight. And taxi operations are the largest source of emissions in a standard LTO cycle. A study showed that up to 72% of the emissions out of the LTO cycle is used for taxi operations. A huge amount of fuel consumption and emissions are from taxi operations. And then another report says fuel consumption from taxi operations is forecasted to cost about $7 billion by 2012 worldwide, and 18 million metric tons of carbon dioxide per year. By the way, these statistics are based on ICAO data bank rates, which has very approximate, high-level approximation solutions. So NASA has done more work on the method development for calculating fuel consumption and emissions for surface operations. So based on the SDX data, which is quite accurate surface surveillance data system, we analyzed each aircraft trajectory so that we divided taxi phase of flight into different states of aircraft. For example, aircraft have stopped when there is a queue build, or aircraft is taxiing at a constant speed or decelerating, or aircraft is accelerating from stop to gain speed. So depending on those states of aircraft, we have to use the different thrust level. So we developed kind of thrust level model based on literature survey as well as pilot interviews. So based on that thrust level, we can easily calculate flow rate and emission indices from ICAO data bank through extrapolation. So we took data from DFW, Dallas-Fort Worth International Airport data for about 3 months in 2008, and then we calculated total average daily fuel consumption and emissions on those taxi operations. So the pie chart you see is the breakdown of fuel consumption for taxi operations. As you can see, there are about 81% of fuel actually is consumed for constant speed taxiing or decelerating type of operation, normal operation, taxi operation. But 18 to 19% of fuel is consumed when aircraft are stopped in a queue and then try to gain speed by accelerating. So up to as much as 18 to 19% of fuel is consumed for those stop operations. So if we can somehow eliminate those stop operations or reduce stop operations as much as we can by making surface operations much more efficient, then there is tremendous gain in fuel saving as well as reduction of emissions and noise. And next chart, this chart shows, again, the same data analysis result, average daily fuel consumption and emissions. So as you can see, not only the percentage of the fuel consumption and emissions on taxi operations break down, but it also shows the total amount of fuel consumed per day and also emissions, basically hydrocarbon and carbon monoxide and nitrous oxide emissions. So for example, for fuel consumption area, there is up to 120,000 kilogram or 40,000 gallons of jet fuel is used for daily taxi operations. So 18 to 19% of that is almost like 7,000 gallons of fuel, jet fuel is being consumed just for stops and go type of situations. So if you do simple math, 365 days a day, per year, so it ends up like $5.5 million of fuel cost is spent just for stops and go situations for Dallas-Fort Worth International Airport situation. So that's quite significant amount of the dollar spent wasted for stop and go situations. So the question is, can we make it better, or can we make surface efficient more operationally? So that is kind of focus of NASA surface research. All right, so surface environmental research that the NASA is conducting is to develop concepts of energy efficient operations and decision support tools to make surface operations much more efficient, and thus will lead to less environmental impact. So we just focus on more efficient operations that will lead us to less environmental impact. And secondly, with that concepts and technology algorithms we develop, we also need to conduct various types of evaluations, including humans in the loop experiments, to evaluate performance of the tools and algorithms and so forth. And then based on that simulations, we can calculate, we can perform estimation of fuel consumption and emissions to verify the environmental benefits out of this efficient surface operations. So in doing so, the group of researchers developed a near-term decision support tool for tower controllers to enhance the efficiency of surface traffic. We call the tool Spot and Runway Departure Advisory, or SARDA tool. The basic concept is to provide an optimal schedule for release of aircraft from ramp area to movement area, which is taxiway, and then provide tactical advisories to the controllers working on the air traffic control tower, basically ground and local controller. So current operations, as you may know, ground controllers issues taxi clearances as soon as aircraft are waiting at the spot, regardless of runway capacity. They don't really pay attention much on the congestion level on either taxiway or runway queue. They just send out aircraft as aircraft are ready to taxi into the taxiway system. So in a nutshell, the tool provides the ground controller with optimal spot release advisories, basically sequence and timing advisory. So it try to minimize the number of aircraft taxiing on a taxiway and runway queue while still maintaining the maximum throughput. So we don't want to run dry the runway queue, but we try to maintain the minimum number of aircraft in the queue, so still we can achieve the maximum throughput. And then in addition to that, the tool also provides the local controller with runway departure and the runway crossing advisories. So in order to maximize the usage of runway, we provide a local controller with a tactical advisory, basically sequence advisories for takeoff and runway crossing for arrival aircraft. So we had done simulation, human-in-the-loop simulation called the SARDA experiment in late April and early May. So what you see is a screenshot of a simulation when the controllers didn't have advisories. So as you see, there is a huge queue build up in the runway queue. At some point, there are like 16 aircraft just waiting and moving very, very slowly, spending lots of extra fuel, and then generating excessive emissions. Compared to that, we also ran the same scenario, which is heavy traffic density scenario, and then we provided controllers, both local and ground controllers, advisories. So as you can see, there are only about 4 or 5 aircraft in the queue, but controllers were able to achieve same amount of throughput without having much difficulty, just to follow the guidance and control advisories. But you may notice that in the ramp area, is a little bit busy than previous case because we haven't really addressed ramp area congestion issues here, because our idea was to meter the departures at the spot rather than at the gate. So in order to address that, we may need to introduce some sort of collaborative decision-making type of scheme so that airlines and ATC can collaborate for pushing back the aircraft. So I am expecting that Chris Brinton is going to address that technology after this. So just a quick initial research, the data analysis shows that number of stops and goes in SARDA experiment showed significant reduction when controllers were using the advisories. For example, first the bar graph shows the total number of stops for departures from pushback to a runway. So first bar is baseline, which the controller didn't have advisories to use, like 7.4 stops per aircraft, versus the 2 other bars next to that shows the number of stops per aircraft when the controllers were using advisory. We had 2 different formats for advisories. One is called timeline advisory, and the other was called data tag advisory, depending on how we display, how we show the advisory, whether in the data block and next to the aircraft call sign, or the timeline type of sequence and timing advisories. In the departure queue, it's very, very significant. On the left lower corner is average departure queue stops. With baseline, without advisory, there was like 5.45 number of stops per average aircraft versus like 2.2 stops per aircraft when the controllers were using advisories. And the ramp area stops were slightly increased, as you may expect. And then there is another other areas of friendly surface operations. As you may see, more airlines are asking pilots to taxi with single engine just running, and then they ask a pilot to turn on the second engine when aircraft are near runway in 2 to 3 minutes before the runway entrance or something like that. And then the second technique is obviously departure metering. So the tool that I just introduced is kind of departure metering, and there are other schemes of departure metering. And then perimeter taxiway can save taxi delay or taxi fuels and emissions in certain conditions. Instead of waiting in a runway crossing queue, just taxiing all the way to the gates. And then there's out-of-box idea, for example, tow-out taxiing, which uses electric power to tow the aircraft instead of using tow bar, tractor. And then other concepts using optimal runway and environmental planner and takeoff roll regulator. Because of time, I'm not going to go through all this. So summary, we developed a method to calculate fuel consumption and emissions of phases of taxi operations, and our data analysis results at DFW show that as much as 18% fuel can be saved by eliminating stops and go situation. Even more, can be done theoretically. And we developed an energy efficient and environmentally friendly surface concept called SARDA. And the SARDA tool, by the way, has been identified as a potential candidate for technology transfer to FAA through the research transition team. So with that, thank you for listening.